Welcome. In this session, we'll learn the behavior of the capacitor voltage at the time of switching. Let's start. In the previous sessions, we learned what happens to the capacitor voltage if we connect a source or disconnect a source from the RC circuit. So in the previous sessions, we learned In the previous sessions, we learned what happens to the capacitor voltage and what's the behavior of VC of t with respect to time as we change the position of this switch from 1 to 2, as we connect the switch from 1 to 2 or from 2 to 1. So if we connect or disconnect a source to this. Now in this session, what we will try to do, we'll check what happens to the capacitor voltage momentarily at the time of switching. Means what happens to this capacitor voltage at the time of switching. Now that we'll observe by studying the VI relationship of this capacitor. We know the capacitor current, the current that flows through the capacitor is given by d VC of t by dt. So we can write this like this: VC of t is in terms of integration minus infinity to t IC of t dt. All right. Now our goal is to learn what happens to the capacitor voltage momentarily at the time of switching. In other words, if we change the position of the switch at time t, so if we change the position of the switch at time t equal to 0, if the capacitor voltage has some value just before this switching, means if the value of the capacitor has some voltage value, let's suppose V naught for instance. So if this is the value, what will happen to this capacitor voltage just after the switching? What will be the value of this capacitor voltage just after this switching? Now again, what is 0? What is the illustration of 0 minus and 0 plus? 0 minus means it is at the time just before this when you perform the switching operation, or suppose it can be, for example, 0.000001. So it is very small. Same way 0 plus can be the time instant just after the switching, means it is the time instant when we just connected this switch, when we change the position of this switch, and you can say it's like this. All right, so this is almost a 0. Now let's see what will happen to the capacitor voltage as we go from 0 minus to 0 plus, or what happens to the capacitor voltage at the time of switching. Let's do it from this expression. So we can write VC of t will be equal to 1 by c integral. Let me break this integral into 2, minus infinity to 0 minus IC of t dt plus 0 minus t IC of t dt. So we have broken this integral into two terms, two integrations, right? So we can write it as VC of 0 plus, because that's what we want to see. We want to see the value of the capacitor voltage at t equals 0 plus. So it will be 1 by c 0 minus IC of t dt plus 0 minus 0 plus IC of t dt. Now what is this? What is this first term? Now this is the voltage stored in the capacitor at t equal to 0 minus. So this will be VC 0 minus plus, sorry, there is one more term. I have forgotten that. There is 1 by c also. Then this is 1 by c 0 minus 0 plus IC of t dt. All right. Now have a look at this integral. This is from 0 minus to 0 plus, means this includes almost 0 time on the time axis, right? If we consider IC of t as a function, and if you say on the x-axis means that is the time axis here. It includes a 0 time interval. So in other words, to have a finite value of this integral, you require a current that is equal to infinity. To have a finite value, finite non-zero value of this integral, then the value of this current should be approaching to infinity. And we know for all practical purpose, that cannot happen. So we know for all practical purposes, or for all practical input sources, that cannot happen. In other words, what I am saying, the capacitor voltage cannot change instantaneously. For all practically existing input sources. In other words, this integration is 0. So we can say VC of 0 plus will be equal to VC of 0 minus. So we can conclude this. In other words, capacitor voltage cannot change instantaneously. Means whatever is the value of the capacitor voltage just before the switching, the value of the capacitor voltage will remain same just after the switching time instant. All right. So capacitor voltage cannot change instantaneously. In other words, the value of the capacitor voltage remains the same just before and just after the switching time instant. But from ideal, we have one ideal source. We have a source that is the impulse signal. If you remember, we have one signal that's referred as the impulse signal, and it is denoted by delta t. And we know the definition of the delta t is like this: delta t is equal to infinity when t is equal to 0, and it's equal to 0 for all other values of time. So this is a very strange kind of a function because its value is 0 everywhere except at one place where the value is infinity. So if we plot this function, so this is our delta t, this is t, and the definition says it is 0 everywhere except in one place where the value is infinity. So it is 0 everywhere for all time instants. It is 0 except at this place at t equal to 0. So suppose this is our 0 minus and this is our 0 plus. So this includes a very large value. So if we put this value here, in other words, if we substitute the IC of t equal to delta t in this, so if we put IC of t here, we'll get VC of 0 plus will be equal to VC of 0 minus, that will be equal, sorry, VC of 0 minus plus 1 by C 0 minus to 0 plus delta t dt. What is this equal to? By using the area property of the delta function, this will be equal to 1. So it is 0 minus plus 1 by C. So this is VC of 0 plus. So ideally, we can change the value of this capacitor voltage if the input is the delta function. But again, this is an ideal function. No source, no practical source can change from 0 to infinity in 0 time. No practical source can do that. All right. Now let's conclude this. What will happen to this energy storage? Now, practically, we said the capacitor voltage does not change. Means whatever is the value of the capacitor voltage just before the switching, the capacitor that will remain the same. So that, in other words, means what is the value of the energy just before the switching? We know that is given by 1/2 of CV square. That will remain the same practically. Okay, the energy stored will be that is same as the energy stored just after the switching instant. But ideally, if I take now the ideal situation, Means if the input, if IC of t is delta t. Now under this scenario, what will happen? If I say VC of 0 minus is equal to 0 and for the simplicity, let's say this is 0. What is the energy? Then energy stored at 0 minus will be simply equal to 1/2 of CV square. V is 0, so it will be 0. Now, if I say this is delta function, then what is the value of, if the input is delta function, what is the value of this capacitance voltage just after the switching? It will be VC of 0 minus plus this 1 by C from this expression, here. So what is the value of VC0 for this example that we have taken? It's equal to 0. So we say this is equal to 1 by C. So what's the value of the energy just after the switching? It will be 1/2 of CV square. How much is V? V is 1 by C. So it will be 1 by C, 1 by 2 C, 1/2 of, sorry, not 1/2 of, 1 by C square. So it will be 1/2 of 2C. So the energy stored just before the switching will be different. The energy that is stored just after the switching. And this is only for this case. This is only for this ideal case. But for all practical purpose, means the examples that we have that will follow next after this class will assume that VC of 0 minus is equal to VC of 0 plus. All right. In other words, capacitor voltage does not change instantaneously.